Okay, welcome to this lectures of our system dynamics and control course. So already in the last lectures, Professor Siva Subramani has taught you most of the things about dynamics modeling, right? Dynamic modeling of the system, including synchronous machines, load modeling, right? And also, he taught you the exciter modeling in the generator. That is also part of the generator. Exciter, then turbines, all these things you already know, right? So now we'll start actually doing how we can represent these machines, because in a system, if we'll see a power system, it is not consisting of one machine, because when you do the modeling of the synchronous machine, you have seen the transformation, DQ transformation, and then you did it. And we should remember that this DQ transformation, what you did, it is only in reference to a single machine, that particular machine where you are doing the modeling, right? So now the question is, if in a system we have many machines, multiple machines, and they're all connected into the network, and how will represent this? Because obviously when multiple machines we consider, they're connected to the network, the frame of reference changes automatically, because previously when we were doing a single machine analysis, in the single machine analysis, the reference frame what you have taken is referred to only that machine, right? With respect to the rotor of the generator. But now we have to choose a reference frame which is common to all the machines, and also it is common to the network, right? Transmission network. Okay, now how we'll represent the synchronous machine under that condition we'll study, and we'll do the analysis as well. So how we'll do it? Now the question is, in order to do the analysis, we must know the terminal conditions of the synchronous machine. So, and through that we can find the interaction of the machine with the network and with other machines, right? So therefore it is essential to find the terminal conditions, and in order to find the terminal conditions, so we need to do the steady state analysis. So under steady state analysis, if we know the voltage, current at the terminal, and considering those parameters, we can go ahead and we can find the interaction of these machines considering those terminal conditions. Okay, so already you have been taught this load modeling, and you know these equations very well, right? Already you know this real power equation, real load modeling for load for real power and reactive power, right? And also this is the induction motor modeling. Already it has been taught to you, the dynamic equation for the induction motor. Okay, there are also uh, the dynamic equations for already you have been taught the synchronous machine dynamic equations, right? So these are the starter equations, right? Already you have derived, Siva sir might have derived, and you have noted all these things. And this is also, these equations, set of equations, they are also related to the, sorry, related to the synchronous machine equations with time constants, right? TDO dash, TDO double dash, TQO dash, TQ double dash, they are all d-axis and q-axis time constants, right? And EQ dash, ED dash already you know. Okay, so beyond also except this, we have the swing equation, which represents the rotor dynamics, right? So the swing equation, all of you acquainted very well, right? And next is your stator algebraic equation. Those are the Flux linkage equations, right? So these are the equations which involve the stator side, right? Stator side equations and also swing equation. Obviously, it is the rotor side equation, but uh, all these are very common equations. Already you have studied all these dynamic equations, right? Now, this equation you might have. This is your uh, voltage regulator equation, which is part of the exciter, right? Okay. And next is your rate feedback dynamics. This is also part of exciter equation. And this is your exciter equation involving the voltage regulator. This is your turbine equation, right? And this is also associated with turbine chest equation, right? Then this is also associated with the governor, right? Governor dynamics. Okay. So these three equations represent your turbine dynamics along with the governor, and these three equations represent your exciter equations, right? Already you have studied this. So now, can anybody tell me? Okay, just leave it. Okay. So now we'll derive the steady state condition from these dynamic equations, what we have studied till now, right? So already I told you what is the importance of the steady state condition, why we want to do the steady state analysis, because we want to find out the terminal conditions of the generator and when it is connected to the network, right? So in the steady state condition, the rotor rotates at synchronous speed, okay? Because under that condition, your rotor speed becomes equal to omega s, right? And since the rotor rotates at synchronous speed, the obviously the damper winding currents, which were I1D, I1Q, and I2Q, there obviously will become zero, right? The damper currents. So since the synchronous generator is in the steady state, so left hand side of all the differential equations will become zero, because if we'll see the differential equations, those are representing the dynamics of the generator. So these all will become zero, right? This, because under steady state, they all will become zero, left hand side. And considering the right hand side equations, we'll find some relationship between these equations, right? So hence these equations can be represented as follows. From those equations, we can derive from the terminal conditions, right? We can see here from these two equations, because this equation will completely become zero because your IO under steady state condition is zero, right? And also VO is zero. Under steady state balanced condition, the uh, zero axis components will all be zero. So considering these two equations and the left hand side of these two equations are zero, considering this, we can find the equation for VD and VQ, right? That is what it is mentioned here, right? VD and VQ. That we got minus RSID minus psi Q, and VQ is equal to minus RSIQ plus psi D. Okay. Then again we'll consider these equations, right? This equation, all the left hand side they are zero. and substituting 0 and again equating this with 0, we'll find, because these components will also be the subtangent components will be 0, right? So just neglecting these things, we'll see that this will be, we'll find EFD will be equal to EQ dash plus XD minus XD dash ID, right? You will see this equation. So your EFD will become, because uh, here psi 1D will become 0 and your EFD will become EQ dash, and other terms are like here ID will remain ID into XD minus XD dash. Okay. So your EFD will become EQ dash plus XD minus XD dash into ID. Similarly, other equations we can find from uh, all other three equations what we had, right? These three equations. Now taking d-axis flux linkage equation in the steady state, what we'll get? D-axis flux linkage equation. D-axis flux linkage equation is here. So you can see here this d-axis flux linkage and q-axis flux linkage equation, and zero axis flux linkage equation will also, it will be 0 under steady state condition. So considering only d and q axis, we'll find this relation, right? So xt minus id, xt into minus id, xmd into ift, right? Okay, so now from these two equations, if we'll eliminate ift, then after eliminating, you will get psi d, right? So psi d in terms of id and psi fd, id and psi fd, and this we know this is equal to xd dash, so it will be minus xd dash id, and this whole term we know this is equal to eq dash. So I can put it minus xd dash id into sorry plus eq dash, right? So similarly, if we'll consider q-axis flux linkage equations, so we can have psi q. Similarly, we can get psi q equal to minus xq dash iq ed dash, right? And if we'll substitute these two, psi d and psi q, in this first equation of the voltages, d-axis and q-axis voltages, right? If we'll substitute these two, then we'll find this equation. So your BD and VQ will become minus RSID, just substituting your psi Q and psi D in these two equations. Now your VD and VQ will become minus RSID plus XQ dash IQ plus ED dash, and VQ will become minus RSIQ minus XT dash ID plus EQ dash, right? Let us then consider the three-phase terminal voltage given in the power unit. So if we'll consider the three-phase terminal of the synchronous generator, then I can give VTA is equal to Vm cos omega st plus alpha, VTB equal to Vm cos omega st plus alpha minus 120, VTC will be equal to Vm cos of omega st plus alpha plus 120. This is a three-phase system. Then if we'll apply Park's transformation on these voltages, three-phase voltages, we'll get again d-axis and q-axis voltages, right? So that will be equal to Vm cos of omega st plus alpha minus theta s, and Vm is equal to Bq equal to Vm sine omega st plus alpha minus theta s. So these two equations you got after applying Park's transformation to these synchronous terminal voltages, right? So theta s is the angle between, already you know this, between the d-axis and the phase AMMF axis. and that we represent omega st plus theta o, where theta o is the initial angle between the d-axis and the phase AMMF axis, right, at time t equal to 0. Noting that per unit RMS value of voltage Vt and peak value of voltage Vm are one and the same. So we know that per unit Vm is equal to per unit RMS value, right? So if we'll write RMS per unit, they are equal because we know this is simple. Vm per unit, we know Vm by V base, right? So Vm by base, sorry, Vm base. So Vm by root 2, if we'll put it, so Vm base by root 2. So that will give me Vrms, right? And Vrms base, right? So that will give me Vrms per unit. So that means your Vm per unit, instead of, because we are doing all this analysis in per unit system. So if we'll consider Vm per unit here, then I can write it, instead of Vm per unit, I can substitute Vt also, because Vm is equal to the RMS value, the terminal voltage, RMS value of the terminal voltage in per unit, right? Okay. So therefore I can write Vd, now your Vd become equal to Vt cos alpha minus theta naught, and VQ become Vt sine alpha minus theta naught. Okay. So, okay. So, okay. Because we substituted here theta s is equal to omega st plus theta o, right? So then from this equation, it can be observed that Vd and Vq are scalar quantities. So due to the trigonometric nature of the equation, if we'll see for Vd and Vq, the terminal voltage also can be represented as a AC phasor, and that AC phasor in fact will have the dq axis as imaginary and real axis, right? So this will become d axis and this will become q axis, and this bt will represent here in vd and d and q axis. It will in fact look like that exactly equal to the real and imaginary axis, right? So therefore we can see, just like an AC phasor, in case of AC phasor, what happens when you represent an AC quantity in a phasor form? Suppose I have a signal, let us say V equal to Vm sine omega t plus theta. So in phasor form I represent this. So I will represent this. So this is my real axis, this is my imaginary axis, and I put here the phasor, that is Vt. Okay, Vt is nothing but in per unit Vt is equal to Vm. So Vt, which is having an angle of theta degree with the real axis, right? So this is how we represent the phasor. So what it indicates? It indicates that this real and imaginary axis is rotating at a speed of omega, right? And along with that, the phasor Vt is rotating at an, this V phasor is rotating at a speed of omega, right? Okay. Therefore, this angle remains fixed. So this is the phasor representation. So similarly here, I can represent these two quantities Vd and Vq in the dq axis, right? So I can write it here d axis and q axis, and I can represent here Vt, which is making an angle of alpha minus theta naught with d axis, right? Exactly, it is similar to representing a signal in real and imaginary axis. Here also your dq axis is rotating at a speed of omega s, right? Okay. So that is what we can say right here. We can see the same thing is mentioned here. Hence, the terminal voltage can be represented as a phasor in the dq axis, right? So therefore, your Vt can be represented as a phasor in the dq axis. Okay. So then here, so representing the same, we'll see what? We'll see that Vt alpha minus theta. This is your phase angle, right? And that is nothing but is equal to Vd plus jVq. Okay, Vd plus jVq. It is similar representation to the real and imaginary axis. And Vt, the magnitude of Vt can be found Vd square plus Vq square square root. Okay, so instead of taking the angle between d axis and the terminal voltage phasor, let us take the angle between the terminal voltage phasor and the q axis. So if I'll take this angle between q axis and this is your d and q, this is your Vt, this is alpha minus theta naught. Okay. And if I'll now take the angle between q axis and Vt, this will be nothing but 90 minus alpha minus theta naught, right? Okay. So let us represent that as delta. Okay. Then what we get? Then we get equation in this form. If we'll write the equation in terms of delta, I can write Vd plus jBq equal to Vt sine delta plus j cos delta. And delta, we know delta is nothing but 90 minus alpha minus theta naught. Okay. So this is equal to the Vt. This is a phasor of the terminal voltage Vt, right? And it is represented in terms of the angle between the q axis and the terminal voltage itself, that is delta, right? This is what it is mentioned here. You can see here in this figure d axis and q axis, and this is Vt. Vt is making an angle of alpha minus theta here, right, with d axis, and with q axis it is making an angle of delta, which is equal to 90 minus alpha minus theta naught. So here Vt is a complex quantity in the dq axis. Exactly, it is a complex quantity in dq axis. Similarly, the stator current It lagging the terminal voltage Vt, if we have a stator current It that is lagging the terminal voltage Vt by phi, that can be expressed in this in the phasor form in the dq axis as this, right? If this It is the terminal current and it is lagging Vt by phi, then I can represent like this, right? Okay. So now if we'll write the current, if we'll represent the current in the dq axis, then I can write Id plus jiq will be. So the current is making an angle of delta plus phi, right? This angle is delta plus phi. So therefore I can write it as It sine delta plus phi plus j of cos delta plus phi, right? Okay. So that is equal to It, and I can in the complex form I can write Id plus jiq. So previously we have derived Vd equal to minus Rs Id plus in the previous slide we already know Vd equal to this and Vq equal to this. Vd equal to minus Rs Id plus Xq dash Iq plus Ed dash, and Vq we know minus Rs Iq minus Xt dash Id plus Eq dash. Already we derived this in the previous slide. And now we know Vd plus jVq is this, right? Now if I'll substitute this Vd equation and Vq equation here in the terminal voltage equation, then what I will get? Vt will become equal to minus Rs Id plus Xq dash Iq plus Ed dash. Just substitute this, we'll get this equation plus j of minus Rs Iq minus Xt dash Id plus Eq dash, right? Okay. Now just expanding little bit and simplifying it, what we'll get this equation finally. And this equation we know under steady state condition, this is equal to 0. Okay. From the steady state equations already we have seen this. And this equation is equal to EFD. Okay. As mentioned here. And just putting these values, we'll find minus RS plus JXQ IT plus JXQ minus XD ID, right? Plus EFD. This is your EFD, right? So this is your real part, not exactly real part. It has also imaginary component. So this indicates your RS is indicating the resistance of the synchronous machine, and XQ is your reactance, right? And is multiplied with current, right? Plus, and we are subtracting it from this equation, this voltage, right? This is your internal voltage from where we are subtracting the impedance drop, and we are getting the terminal voltage of the synchronous machine, right? So we know this EFD is equal to XMD by RFD VFD, that is equal to XMD IFD, right? So if we'll substitute EFD as XMD IFD, then your equation becomes J of XMD IFD minus XT minus XQID, that is equal to nothing but BT plus RS plus JXQID. So this is your drop, impedance drop. This is your terminal voltage, which is added. When it is added, this will give us the internal voltage of the generator. That means this gives us the internal voltage of the generator, right? Okay. So now if we'll see the nature of the internal voltage behind the reactance XQ, that is in fact in the imaginary form, which is lying in the Q axis, right? Because it is J times this. It is a complex quantity having only imaginary term. That means it is lying in the Q axis, right? Okay. So that is what we can see. Let the internal voltage of the synchronous generator be represented as this. So internal voltage EQ is represented as this, let us say. And the magnitude of the internal voltage is this XMD IFD minus XT minus XQID. Or in the Phasor form, I can write like this with it is a complex quantity having only imaginary term, right? So then I can write XQ, the complex XQ equal to VT plus RS plus JXQIT, right? So now this is your complete equation, which in fact gives the equation of the terminal at the terminal of the generator, right? So therefore, I can represent the equivalent circuit of the generator like this. This is your internal voltage EQ. This is your XQ, right? RS, this is JXQ, and current IT is flowing in this. So I can write the terminal, the internal voltage equation as from this circuit also. If I'll write it, it is VT plus RS plus JXQ into VT, right? So the same thing has been represented here in the vector form. We can see here, because your EQ is lying in the Q axis. We can see here, this is your EQ and this is your VT, which is added up with RSIT plus JITXQ, which gives us EQ, right? And VT has two components. One is VD, which is lying in D axis, and other one is VQ, which is lying in the Q axis, right? And similarly, IT, which is lagging VT by phi, IT has two components. One is ID and IQ, right? Which both are lying in D axis and Q axis respectively. Okay. So now, from the above equation, what we can say that it can be observed that the internal voltage EQ is aligned along Q axis as shown here. Since EQ is aligned along Q axis, it is at an angle of delta, right? Obviously, because Qx is making an angle of delta with Vt, so therefore EQ is making an angle of delta with Vt, right? So this angle delta is called the generator rotor or load angle, because you can see here this is the angle between uh, the internal voltage and the terminal voltage. Okay, this angle in fact known as the load angle or rotor angle. Okay, because through this angle, when we can see, if we'll take the terminal voltage angle, terminal voltage as the reference voltage, if we are considering a single machine, under that condition, your internal voltage, whatever angle it is making with the reference, right? That is the internal, that is the rotor angle or the load angle, right? And this load angle can be computed if real power output PT, reactive power output at the terminal QT, and the terminal voltage VT of the synchronous generator are defined well. So if it is given, suppose you are given the terminal complex power, that is PT plus JQT and VT, then you can find out this delta, right? So let us take the terminal voltage as the reference here, because in a single machine case, the terminal voltage is always taken as the reference. But when there are multiple machines, the reference changes, right? Obviously. So then we can locate Q axis at an angle of delta with respect to the terminal voltage phasor. Okay. So now if your power and voltage is given for a particular machine which is connected to, let us say, infinite bus, the terminal power and voltage is given, then I can write IT is equal to obviously the complex square, the magnitude of the complex power divided by Vt, terminal voltage magnitude. That will give me the magnitude of the current, and the phase angle of the current obviously will be cos inverse of Pt by Vt, right? We know Vt cos phi is equal to Pt, right? This is the power factor angle, right? Okay, so EQ bar, now I can write it. If I take terminal voltage as the reference voltage, then I can write EQ as equal to Vt plus Rs plus JXQ IT. So IT has an angle of minus phi, right, with respect to the voltage. So voltage is taken as the reference here. Similarly, the phase angle or the rotor angle can be written. Rotor angle is the angle of the EQ, right? Because whatever angle this EQ, the internal voltage making with the reference, that is known as the internal, that is known as the rotor angle or the load angle. Okay. So this internal voltage angle can be found from this equation, just expanding this equation in the complex form and taking the tan inverse of the imaginary part divided by the real part. That will give us the internal angle. Okay. Okay, now in case of steady state, no load condition, suppose under no load condition, what happens? The starter currents ID and IQ becomes 0, right? Because IT is 0, so ID and IQ also becomes 0, and therefore the following expressions hold. If we'll substitute ID, IQ as 0 in your steady state equations, so we'll find all these condition. All this is the condition. Now all these equations become VQ equal to EQ equal to EQ dash equal to EFD equal to VT equal to psi D equal to XMD IFD. So this is under no load condition, right? So this EQ is your internal voltage and VQ is your terminal voltage, Q axis terminal voltage, EQ is the internal voltage, right? And VT, we know this is the terminal voltage. So under no load condition, your VT becomes equal to VQ, whereas VQ and EQ, they're lying in the Q axis. Okay. So therefore, what happens if Vt is becoming equal to Vq? That means Vt is lying with Vq. That means it becomes, that means your delta becomes 0 under this condition, right? So that means under no load condition, your load angle or rotor angle becomes 0. When the load changes from no load to certain load value, then your delta increases gradually. Okay. So we must remember this, that under no load condition, your load angle or the rotor angle is always 0. Okay, therefore it is known as load angle, because as the load increases, this angle also increases, varies, right? And under this condition also, under no load condition also, your Vd becomes equal to Ed dash equal to psi q is equal to 0. Because as soon as your Vt has two component, Vd plus jVq, and when your Vt becomes equal to Vq, then obviously your Vd becomes 0, right? So as Vd becomes 0, your Ed dash, they're all related equation. You can see it. Just substituting, you'll find Ed dash equal to 0, psi q also becomes 0. Okay, hence in the steady state no load case, the internal voltage EQ and the terminal voltage VT are one and the same, due to which the load angle delta becomes 0. Okay. And as the load increases, the load angle delta also increases. Therefore, it is known as the load angle. So it can also be observed that for 1 per unit internal voltage or the terminal voltage in steady state, no load condition, the field current will be this, right? The field current equation we know, right? IFD is VFD by XMD, right? So EFD is nothing but equal to your VT. So therefore, your this will become 1 by XMD. Okay, so now up to now we saw that how in the DQ reference, right, how the terminal voltage is represented, voltage and current, they're expressed in in DQ reference frame, right? And what is the internal angle, all these things we discussed. Now we'll see the conversion from DQ axis to common reference frame. That means from machine reference frame to common network reference frame. Because whatever we are discussing now, it is all in the machine reference frame. Whatever DQ axis we have considered, this is in the machine reference frame. It is not common reference frame. So when we are considering a huge network connected with many machines, that means the reference frame of reference changes, right? So for each machine, individual machine, it has different references if we'll consider, but it has to be transformed to a common reference frame, or we call it sometime network reference frame, right? So that means we'll transform this to the reference frame which is associated with the slack bus. Slack bus or reference bus we call it, right? You must be studied slack bus, reference bus, right? This terminology you know when we studied load flow in our power system course. All the BTech students also they have studied and others also know. So with respect to this slack bus or the reference bus, we'll make the common network reference frame and we'll transform each of these parameters to the common reference frame. Okay, so that is a conversion from DQ axis to common reference frame. Now you know the delta is this. Say delta is the angle of the internal voltage, that is tan inverse of this, right? Already we have seen, we have derived this. So the load angle computed in this equation is with respect to DQ axis. It is for a particular generator, right? So already we know this delta is nothing but it is EQ or Q axis, D axis. This is your BT, so this is your delta. And we considered here VT as reference, right? Because for each machine, the terminal voltage if we are considering a single meson system, the terminal voltage will act as the reference for that particular meson. But if we are considering a multi-meson system, then our reference changes. Our reference becomes the slack bus or the reference bus. So therefore, now we'll consider delta as the angle between the EQ and the reference voltage that is associated with the slack bus or the reference bus, right? But here this delta indicates it is the angle between, that is the angle for a particular generator, that is angle between EQ and or Q axis and the VT, right? Okay. But in case of multi-meson system, there should be a common reference instead of multiple individual generator references. So usually in a network with multiple mesons, yes, somebody is telling something. Usually in a network with multiple mesons, a slack bus or reference bus is defined and all other bus angles in the network are defined with respect to the common reference bus already I discussed. So hence there should be a conversion from DQ axis of individual generator to common reference in real imaginary axis. So for that, a reference bus will frame a common reference that is having a real and imaginary axis, and then we'll transform this or will convert this DQ axis to the common reference frame. So now we can see here this VD and VQ, they are showing the DQ axis of a particular generator or particular meson, okay, for a particular meson, and this R axis and I axis indicates these are the real and imaginary axis for the reference bus. Okay. Now under steady state, both this DQ axis and RI axis, R and I axis and D and Q axis, both are rotating in the synchronous speed. Therefore, there will be no change in this angle, load angle, it will be constant, remaining constant, right? So this load angle now will be what? It will be the angle between the Q axis and the R axis, which is the reference voltage, right? So if we'll take the reference voltage in the slack bus, this will lie in the R axis. So therefore now your load angle changes. So delta is nothing but it is the angle between the Q axis of that meson, or you can say EQ, the internal voltage lying in this axis, EQ and VR or R axis, or you can say Q axis of the meson with respect to, that means delta is the angle between the Q axis of the meson and R axis of the network. Okay, so this is the delta, right? Now the load angle previously was defined as angle by which Q axis leads the terminal voltage, but now it should be defined as the angle by which the Q axis leads the common reference R axis. Okay. So instead of in steady state, what happens? Both DQ axis and RI axis rotate at electrical synchronous speed. Hence the load angle in the new reference frame is fixed, right? Therefore it remains fixed for a given load condition. Okay, now if I'll write the equation, your VR will be equal to, how I can write, VT cos alpha. If VT is making an angle of alpha with respect to, VT is the terminal voltage of the meson, and let us say the VT, the terminal voltage of that particular meson, is making an angle of alpha with respect to the reference voltage, which is lying in the R axis, right? So then I can write VR is equal to VT cos alpha, Vi equal to Vt sin alpha, and that is equal to, I can write it as Vd sin delta plus Vq cos delta, because if we'll see what is the angle made by this D, right? this VD, this is your VD, this is your VD, VD, D-axis and sorry, this is your VD, sorry, already it is there, VD, and this is your VQ, right? Okay, so now I can find how much this VD and VQ or VR and VI, if I'll represent in terms of VD and VQ, how it will look like. So your VR will be equal to VD. How much? So this will be VD. So VD is here and VD is making an angle of, this angle is how much? This angle is how much with respect to VR? VD is making an angle of R axis. How much is the angle? That will be, this will be your 90, sorry, delta minus 90 degree, right? And here also the same case. This will also, VQ will make an angle of delta minus 90 degree with I axis, right? Okay. So therefore, your VR in terms of VD and VQ will be VD sine delta, right? VD cos of delta minus 90 will be VD sine delta and VQ cos delta, right? Okay. Similarly, your VI in terms of VD and VQ will be minus VD cos delta plus VQ sine delta. Okay. So now VT, you know, if we'll represent in the complex form, VT e to the power j alpha, then I can write it as VR plus JVI. So then substituting these values here, VD sine delta plus VQ cos delta, here you substitute in terms of VR and VI, right? If we'll substitute these values, we'll get finally, just segregating, we'll find VD plus JVQ into sine delta plus J cos delta. So that will be equal to VD plus JVQ e to the power J of delta minus pi by 2, right? So now what it represents is that, again, if we'll say VD plus JVQ, I can write it VD plus JVQ in terms of the terminal voltage, then I can write VT into e to the power j of alpha minus delta plus pi by 2, which is nothing but is equal to Vt sine of delta minus alpha, j of Vt cos of delta minus alpha, right? So now if we'll consider current, obviously similarly current is making an angle of phi with Vt. So similarly we can write the current expression. Hence, whenever the uh, starter voltage current expressed in dq axis needs to be transformed to the network frame of reference, that is the Ri axis, then we need to multiply the complex voltage or current in the dq axis with the factor of e to the power j delta minus pi by 2, where delta is the load angle, that is the angle between the q axis of the individual generator with respect to the common reference frame, right? So when we transform this voltage to this voltage to the common reference frame, we need to multiply e to the power j of delta minus pi by 2, right? So this is all. So we'll next class we'll discuss little more about this, how a single machine infinite bus system, when it is connected to the infinite bus, how we can represent these equations. Okay, then we'll move ahead. Okay, so we'll stop here.